Hello, welcome to Block 2. In this block we're going to build on some of the ideas introduced in the first block of the course. For example, do you remember this?
If I wanted to describe the ballista mathematically, then all we've got to do is to find the trajectory. And then, for any given distance, we'd know the height that the ball passes through.
Norman was demonstrating a model of a ballista. The trajectory of the ballista turned out to be the graph of this function. And from the graph you can see straight away lots of interesting features of the function. You can see where it reaches its maximum height. And you can see for how far the projectile is climbing. That's this part of the graph where the function's increasing. You can also tell at once that the function's not one-to-one. You can get a lot of information about a function by looking at its graph. But if you were just presented with the function and had no idea of the graph, how could you tell what its graph was like? That's the kind of problem we're going to look at. If you're given a function, what can you say about its graph? Now this function's quadratic, and one of the nice things about quadratics is that all their graphs look much the same. That is to say, if you start with the graph of the simple quadratic y equals x squared, then by scaling and translation, you can get the graph of any quadratic function. Here's the graph of y equals x squared. What effect will scaling in the y direction have on this graph? Y scaling by factors greater than 1 makes the curve steeper. Scaling by smaller numbers flattens it out. If you scale by a negative factor, it turns the graph upside down. The negative scaling minus 1 is just a reflection of our original graph. Scaling lets us vary the shape of the curve. When we've got a particular shape, we can apply a translation. Remember, the way of describing a translation is to mark where the origin gets moved to. Translations let us move the graph to any position we want. In this way, we can get the graph of any quadratic function. These operations of scaling and translating, applied to y equals x squared, give the graphs of all quadratic functions. Now we're interested in finding the graph of this function. And we know we can get it from the graph of y equals x squared by scaling and translation. But by what factor must we scale? And by how much must we translate?
So what we're looking for is an algebraic technique to find out precisely what scaling and translation Mike needs. Well, you've actually come across such a technique before. It's called completing the square. Let me remind you that if you start off with y equals 4x minus x squared, and you apply that technique, you get something like this. Now, I've actually rearranged it slightly. I've brought the 4 to the other side, and I've done that because it's very suggestive. In this form, it looks very much like y equals x squared. And that tells me really what I need to know. It tells me that if I start off with y equals x squared, and then if I scale by minus 1 in y, and translate to the point 2, 4, then I end up with precisely the function I was looking for. Now, graphically that means if I have y equals x squared and I scale by minus 1 in the y direction, that's just reflection in the x-axis, and then I translate the origin to the point 2, 4, then I get precisely the graph that we were looking for.
So this technique of completing the square gives us the graph of 4x minus x squared from the graph of y equals x squared. And from the graph, we can spot a number of features of our function. We can see at once the maximum value of the function. And in this case, the maximum lies above the x-axis. And this means that the curve must cross the x-axis twice. And so that for x minus x squared equals 0, for x equal to these two values. We say that the corresponding equation for x minus x squared equals 0 has two solutions. Now, this technique of completing the square will work for any quadratic function. Putting it in completed square form allows us to find a scaling and a translation that transform the graph of y equals x squared to the graph of the function we want. Now, if the graph of the function had looked like this, then we would have had a minimum value. And the minimum is above the x-axis in this case, so this graph doesn't cross the x-axis, and there'd be no solutions to the corresponding equation. So we have a technique that works for any quadratic function, and we can use it to find out what the graph looks like. This technique allows us to spot properties of the function which weren't immediately obvious, like the number of solutions of the corresponding equation. Now, let's look at something a little more complicated. Let's look at cubics. This is a cubic. It starts off with an x cubed term. What does its graph look like? In particular, do we have techniques that allow us to find the graph by scaling and translating some basic graph? Well, to get a feel for the problem, let's have a look at some cubic graphs. Let's start by looking at a few of the simpler cubics. A negative coefficient reflects the graph. Now introduce an x squared term. Subtracting x squared, the graph develops a peak and a trough. A larger coefficient increases the size of the peak and trough. Let's move on to x terms. We can flatten the peak and trough out. Finally, the constant on the end moves the graph vertically. Just from the few changes of coefficient we've used, we've got quite a lot of different looking graphs.
So we seem to have a variety of shapes for cubic curves. Some of them are increasing to a peak like this one, decreasing to a trough, and then increasing again, whereas this one is increasing all the time. Well, one thing we can say is that they all cross the x-axis at least once. Well, this crosses it once only, and others cross it more than once. Well, the question is, given a cubic equation, what can we say about its shape? Well, what made life easier for quadratics was the fact that every quadratic is just a transformed version of y equals x squared. Could it be that every cubic curve is just a transformed version of y equals x cubed? Well, let's plot y equals x cubed and see the effect of scaling and translating on it. Let's try a y scaling. A large positive scaling stretches the graph upwards. A smaller scaling squashes it down. Negative scalings are like reflections. But we've seen cubic graphs with peaks and troughs. Let's try scaling in the x direction. Scaling y equals x cubed doesn't seem to produce a peak or trough. How about translations? Translations don't help either. These graphs still don't have peaks or troughs. Well, it appears that no amount of scaling and translating will put peaks or troughs into y equals x cubed. If that's true, then we ought to be able to construct a mathematical proof of it. Well, to do that, let's take as an example of a cubic with peaks and troughs x cubed minus x, and you've plotted this graph earlier on in the unit. Now, what we want to prove is that we can't scale and translate y equals x cubed in order to get this graph. Or conversely, we could prove it the other way around, that you can't scale and translate y equals x cubed minus x in order to get y equals x cubed. Now, what difference can you see between these two graphs? Well, if I draw a horizontal line across it, it cuts this graph in 3 places. Now that means that this graph is not one-to-one. But any horizontal line on the other graph will always cut it in only one place. That's because y equals x cubed is one-to-one. Now, let's just concentrate on this bit of the line. So what I've drawn here is a horizontal chord to the curve. Now, before the program, we asked you to show that when you scale and translate a horizontal line, then you're going to end up with a horizontal line. So, when we transform this graph with its horizontal chord, then the graph we end up with will always have a horizontal chord. And so no matter what we do, the resulting graph can never be made one-to-one. So x cubed minus x can never be made one-to-one, so it can never be transformed into y equals x cubed. And because all these scalings and translations are reversible, we can't transform y equals x cubed to x cubed minus x. So, it seems that we have at least 2 types of cubic graphs. Firstly, there are those which are not one-to-one, like that. And then there are the ones that are. For example, those. And what we've shown is that we can't transform this non-one-to-one graph to get any of these one-to-one graphs, and conversely, we can't transform this one-to-one graph to get any of these graphs. But that still leaves the question open as to whether I can get all these one-to-one graphs by transforming just y equals x cubed, and similarly, can I get all of these non-one-to-one graphs by transforming, for example, this graph.
Let's concentrate on the graphs of cubics that are not one-to-one. Now, x cubed minus x is a simple example of a cubic which is not one-to-one. Could it be that by scaling and translating this graph, we could get all the cubics which are not one-to-one? Well, let's look at the sort of graphs we would get by scaling and translating this graph. Y equals x cubed minus x has a peak and a trough. Scaling in the y direction changes the heights of the peak and trough. Notice that scaling in this direction doesn't move the points where the graph crosses the x-axis. Scaling in the x direction widens or narrows the graph. The peak and trough move further apart or closer together, but their distance from the x-axis doesn't change. So if we start with y equals x cubed minus x, a y scaling will make the peak and trough as big as we please, and then an x scaling will move them to any distance apart. Now a translation will move the graph without changing its shape. You'll find in the notes following the program that you can in fact transform the graph of y equals x cubed minus x into the graph of any non-one-to-one cubic by combining 2 scalings and a translation.
So all the cubic functions that are not one-to-one, well, they all go together. They can all be got by transforming y equals x cubed minus x. Now, what about the 1-1 cubics? Do they form a single class? Well, y equals x cubed is in that group. So could it be that I can get all my 1-to-1 cubics by transforming y equals x cubed? Well, another cubic curve that you've actually looked at previously is y equals x cubed plus x. So we can see that this is 1-to-1, and the specific question I'm asking is, can I obtain y equals x cubed plus x by transforming y equals x cubed? This is y equals x cubed plus x. The graph of x cubed is wider. We can stretch the graph in the y direction. But it doesn't get very close. We could try x scalings instead. But on x cubed, these just have the same effect. Let's add a translation. Translations clearly don't help us either. Well, we don't seem to be having much luck in trying to match these two curves. Perhaps there's some essential difference between them that we should be able to spot. Well, they're both increasing curves. But look at y equals x cubed. It's increasing, then it seems to try and level out at the origin, and then it goes on increasing again. But y equals x cubed plus x is increasing all the way up. It doesn't try to level off at all. Well, that doesn't sound very precise, so I ought to try and make that a bit more mathematical. And what it seems I'm trying to do is I'm trying to talk about the slope of the curve. And to do that, I talk about the tangent. Now, that's the line which just touches the curve. So what we ought to do is to explore the behavior of tangents to these curves. We'll start with y equals x cubed plus x. A tangent here has a positive slope. Moving along the graph, the slope of the tangent remains positive, but it gets smaller as it approaches the origin. At the origin it has slope 1, and it's the smallest slope we can get, but it's still positive. Beyond the origin, the slope of the tangent increases again, so tangents to this graph always have a positive slope. Now look at y equals x cubed. Once again, we start with a positive slope. At the origin, the tangent has its least slope. It's horizontal, so it has slope 0. Beyond the origin, positive slope again. So there's a horizontal tangent at the origin, and we know something about horizontal lines. If we scale, or translate this graph, although it will change its shape and position, it will always have a horizontal tangent. No amount of transforming y equals x cubed can get rid of this horizontal tangent. But x cubed plus x has no horizontal tangent. So we cannot transform x cubed with its horizontal tangent to match x cubed plus x, which has no horizontal tangent. So x cubed and x cubed plus x are not transforms of one another. And they're distinguished by the fact that y equals x cubed has a horizontal tangent and y equals x cubed plus x hasn't. Now, we can sort out this group of one-to-one functions into two classes, those which have horizontal tangents and those which don't. And in fact, all the graphs with a horizontal tangent can be obtained from y equals x cubed by scaling and translating, and all the ones that don't have a horizontal tangent can be obtained from x cubed plus x. And you'll find the algebra for that in the unit.
And that's the complete classification of all cubic graphs. Every cubic graph can be got by scaling and translating one of these three basic graphs. One class comes from y equals x cubed plus x. They're all the ones with no horizontal tangent. Then there's the class from y equals x cubed. These all have one horizontal tangent. And finally, there's the class from y equals x cubed minus x. These all have peaks and troughs. And there's a connection here between peaks and troughs and tangents. You see, at a peak, we have a horizontal tangent. And at a trough, we have a horizontal tangent. So all the graphs in this class have two horizontal tangents. So we can classify every cubic graph just by its number of horizontal tangents. Every cubic has either 0, 1, or 2 horizontal tangents. And so cubic graphs come in these three basic shapes. And once we've established which shape we're dealing with, we can scale and translate that basic graph to get the graph we want. Well, let's try that out in practice with an example. Before the program, you showed that our original expression could be written like this. If you take the 2 on the end across and divide by 2, you're left with something recognizable. It's this minus sign that gives us the clue. It tells us we're dealing with an x cubed minus x type of cubic. Now, a y scaling by 2 and a translation to minus 1, 2 will take us from y equals x cubed minus x to our original expression. So graphically, if we start from the graph of x cubed minus x and firstly scale by 2 and then translate, we get the graph of the function. Note that this trough has come above the x-axis, so the graph crosses the x-axis just once. That's something we could have established algebraically. This trough comes from the trough on x cubed minus x. And this trough has its minimum value when x equals the square root of 3 upon 3. After the program, we'd like you to work out the coordinates of the point at the bottom of the trough and find the point it transforms to. Now, how do I know that this trough occurs at root 3 on 3? Well, that's something you'll find out in Unit 4 of this block. And the way you'll find this trough involves tangents. You see, the trough occurs where we have a horizontal tangent.